My name is Grant McAllister. I'm a senior principal engineer with Amazon RDS. I work on Aurora as well as the other RDS engines. Today we're going to talk about, in this session, Aurora Postgres. We're going to do a deep dive into how it's different than sort of standard or regular Postgres and why you'd care about those differences in your application or running your database. So the first thing to realize is we have two offerings in the RDS Postgres universe. The first being RDS Postgres, which is Community Postgres, runs on EBS, pretty standard. And then we have our own version, Aurora Postgres, that runs on top of Aurora storage, our database-aware storage. So that's going to be part of what we're talking about in this presentation today. But there's a lot of commonality, and the first one you'll notice is that the client protocol and the language and everything is the same. So you can use the same applications, same clients with either of these. And they support a lot of the same features. So for example, they support versions 9.6 all the way up through version 12. They have the same extensions. They have backup recovery, high availability, security, all the things you see listed on the slide. Recently, we've added support for major version upgrade on Aurora Postgres. So this allows you to move from an older version like 9.6 all the way up to 12 and get some of the new features that I'll talk about in this presentation. So let's get started by talking about the base architecture of Aurora Postgres. So what you see here is 3 availability zones in a region. And this is important because our storage in Aurora is across all 3 of these. So that means it's durable no matter what's happening. And the blue is sort of a logical construct of that storage. In the physical, we see these gray boxes, and those are Aurora storage servers. And when you ask for a cluster, you get this read-write node that your application can connect to. But we also allocate this storage for you. And what you see is these chunks, so they're 10 gig segments that are allocated across these different storage nodes. And the 6 different colors represent the 6 copies that we keep of this storage. So why 6? Well, this allows us to have 2 copies per availability zone for great durability and availability. Now we only need 4 of these, so when we do a write, we write to all 6 places, but only 4 of them need to come back for us to say it's durable and move on. This allows for better performance while still achieving the durability we want. But the cool thing is we only read from 1, so we don't have to do a quorum read. And we can typically read from the closest one, which will be fastest, so that's a nice advantage as well. So what happens if one of those writes doesn't make it to one of these segments? Well, we have peer-to-peer gossip that'll just repair that one missing write and help it catch up. If we lose a whole node, what we'll do is we'll copy segments from 1 or more of the machines to a new segment. You can also, the nice thing with Aurora is you can have read-only nodes. And I don't really call these replicas because the thing you'll notice is the storage is not copied. You use the exact same storage you would to run your read-write node. Now, how we do this is we actually do asynchronous invalidations and updates to the in-memory version on the RO node to keep it, asynchronously current, which allows you to query from it, but you don't actually have to do all that extra writing. And of course, you can have up to 15 of these in different availability zones with different applications pointing to them. In the case of a failure of an AZ or your primary read-write node, what we're going to do is we're just going to promote one of the read-only nodes and you're back up and running and writing your applications going forward. So that's really nice. So with this storage model, we get some really nice advantages. And one of them that I really like is called fast clones. So let's say you've got a reporting application that you're building and it needs different indexes and a whole bunch of different tables materialized. And you're like, I don't really want to do that in my primary database. Now, one of the options would be I can do a snapshot, I can restore, and I can build that on a regular basis. But with Aurora, what you can do is you can do a clone. And this is really nice, like assume your primary storage is 32 terabytes. If you were going to make a copy of that, that's 32 more terabytes. Instead, with clones, what you get is you get this virtual storage. So we just have pointers to start with to the original storage. So when you want to do something, you can just ask the clone to do a read, and it's going to read from clone storage. But in actuality, that's just a pointer, so it's actually going to read from the primary storage. There's no duplication. When you do a write, on the other hand, now we're going to change the storage. So in that case, we have to do a copy on write and make a local copy for the clone. Now the clone can write new blocks, that's fine. They're only going to show up in the clone's volumes. And the primary can continue to write, and they're only going to show up in the primary. So this isn't some replication, they're split. When the original primary does a modification, we're going to do, again, copy on write and make that difference. So you can see that this allows you to have an inexpensive copy of your database to do all kinds of interesting things, including tests or other one-off use cases. So let's keep going into the architecture. So let's talk about sort of our log-based storage and how that changes the database. So the first thing we did was we removed the log buffer. So I'm showing on the left stock Postgres. showing some queued work, some commits in purple, and writes in blue. So those go into the log buffer. Now, before the log buffer can sync to storage, it has to get locked. So it locks, and if new queued work shows up, it can't enter because the log buffer has to flush to storage and be acknowledged, and then the new queued work can happen. Now, this causes a delay, which can cause loss of throughput. Conversely, over in Aurora, what we do, as things come in, they just flow down. So you can see those 4 transactions, that one write just flow down. But of course, we need to know if this is durable, right? So we have a durability tracking mechanism. This allows us to understand how many of these transactions or writes have actually been acknowledged. So we see now a couple of them went to 2, some at 1, some at 0. Now, if those sessions are trying to do additional work, what's going to happen is, like F, for example, is on the session with E. E was just a write. We don't need to wait for a write. We can just send a commit afterwards, so that can flow down. But if you're queuing up a commit, you can't do that in a relational database. You have to wait for the previous commit to acknowledge before you can send a new commit. So we need to get to durability of 4. So we start waiting for that to happen. And what we see is that we're only at 1 right now, so we can't actually have that acknowledged. So we've got to wait until more of these versions get stored. So now we're at 4 on A and we're at 4 on C, but we still haven't acknowledged C. Why is that? Well, because this is an ordered database. It's a relational database. So we actually have to wait for B to get to 4 before we can acknowledge. Once that happens, then the new commit can flow down and we can start tracking it and see when it gets done. So that's how we work with writes. The other thing we do is we write a lot less with Postgres. So let's look at how Postgres works by default in the community. Let's say we have this block in memory. We have a tuple version 1, and then we add a change to it. So now we have a version 2. Those are going to go to the wall stream, but we're also going to inject a full block into the log, or called a full page write. And the reason Postgres does this is the first time after you touch a block after a checkpoint, you have to eject a full block, and I'll explain why in a second. So when you do another change, we haven't done a checkpoint, so then we just have to do that tuple into the wall. So that's nice and light, right? So at some point we're going to do a checkpoint, as well as we're going to archive this wall off to disk for durability and to be able to do point-in-time recovery, or PITR. So that's all great, but when you do the checkpoint, in Postgres, typically it's an 8K write. That's the basic block size. But the operating system does 4K writes. So one of these writes could be lost in, for example, a host crash. And at that point, you'd have what's called a torn or split block, and this would be corruption, be hidden corruption. So you can't have that. So Postgres has this mechanism, full block writes, to alleviate that. So on recovery, it's going to take that full block out of the log, and it's going to place it over that damaged block. So this is great, works great, 100% reliable, but this means there's a lot of stuff in that wall. Recovery can take minutes, which is really bad if you've just had a crash, right? Your manager's probably in your room yelling at you about this. So in Aurora, it's quite different. We have that same update, same tuple. When that second tuple is in block in memory, we send those log records to Aurora storage. We don't send any full blocks. There's no checkpointing. When version 3 comes in, same thing, just goes to the storage. So we have no engine checkpoints, no full page writes. You can see how much less work we're doing on Aurora. Now, of course, in the background, we still have to coalesce those log records into blocks, but it's continuous and it's parallel. So there's, we can get a really high level of throughput. Now, the nice thing is that means we've reconstructed all the blocks ahead of time. So if there is a crash, the recovery takes seconds, not minutes. And of course, we're backing up all these logs and blocks so we can have backup recovery and PITR available continuously. So let's dive into one of the storage servers. So we're going to look at one of those in particular, those gray boxes on my original slide. So we have our read-write node, and we start a transaction A. It comes into the incoming queue. Now that's in memory, so no problem. We're not going to acknowledge that yet because it's not durable. Once it makes it to the hot log, which is the durable portion, then we can send an ACK back. So this would be one of the 6 acknowledgements that we'd expect from the different storage servers. Now another one comes through, C here, gets the hot log. But we notice, wait, where's B? Because these should be ordered. So we can ask one of the peers to give us B, and it'll send us B, and now we have the continuous range. So at this point, this can go into the update queue and be ready to be staged to a data block. And this is where we're doing this coalescing. So we're taking those log records and we're making a new block. So both those log records and the blocks are continuously backed up to S3. This supports how we do backup and recovery for Aurora. But the nice thing is these data blocks look exactly the same as they do in Postgres. So when Aurora asks to read that block, it's not reading log records, it's just reading blocks. So this is fundamental, just basic Postgres reads. So let's talk a little bit more about backups. So classically, when you think about backups, you think about backing up every night of the week, a snapshot, and then picking up the logs. But that's not what we do in Postgres version of Aurora. So what we have here is just 16 blocks, right, on storage in Aurora. But we're going to make some changes, right? We're going to run our database. So we get 3 updates to block 1. So that's in blue. But at some point, we're going to coalesce those, and we're going to actually make a new block version of 1 to actually have on storage. And this is what happens over time. We get some logs and some blocks. So when we want to do a restore, let's say at this time that I've shown in the red line, what we can do is we can just pull the latest blocks from the different points. So we pull, block 8 and then block 2. So we can pull the various blocks from all the different times. So we don't need an actual snapshot. All we need is to pull the latest blocks. Now, what happens if we try to do this on a point where, for example, we don't have a full block? So in 6, we have a full block, but block 2 just has a log record. So what are we going to do then? Well, we can coalesce on the fly, make a new block out of that, and therefore we can pull all the blocks together. So what this shows is that we don't actually have to materialize all the blocks to allow us to get to any point in time with our backup and recovery. Let's talk about some of the changes that have happened in scaling with Aurora recently. So here I'm back to my regular diagram showing storage and showing the segments in storage. So this might be how your cluster starts off, but in actuality, you're thinly provisioned. So that means you don't actually get all that space and you're not charged that space. You're just charged for what you're using. So if you're using, a couple gig, that's all your cluster is going to be. And as it grows, basically your storage will grow behind it. And previously we supported up to 64 terabytes, but our customers asked for more space. So we've grown now to 128. So you don't actually have to think about growing your storage or worrying about space. You just have it available for you. One of the other really nice features that's been introduced by the Postgres community is their support of sort of native partitioning. This allows you to manage much larger tables and indexes in a much friendlier way so that you don't have to deal with, let's say, a 2 terabyte table. They've added foreign key support so you can enforce those now on partitions. There's list, range, and hash style partitions, and you can attach these in multiple levels. You can have range and hash, list and range, any combination that you'd like with different levels to support your use cases. And one of the best parts is you can now attach these without a lock. So when you add a new partition, it doesn't cause a lock on the main table. So there's no application interruption. So here I'm just showing a sample table for maybe an application where I have a door knocker with a camera in it and I want to record all the door knocks, right? So I've created the main table and the 3 partitions, and they're hourly partitions. And I'm going to keep 24 of these. So I'm just going to keep a day's worth of this. When we describe this in Postgres, we can see we have the standard Postgres definition, but then it shows you the partitions. And you're going to create and drop these on a regular basis. In practice, how does this look? So if we start here and we're going to look at a CloudWatch metric. So my orange metric is my Aurora storage. So this is how much I'm being billed for by Aurora. The blue is a custom CloudWatch metric that is essentially showing the inside database metric. So if I queried inside Postgres, this is the result I would get for how much storage I'm using. These typically at the start are going to seem basically the same. So I start off and I create a new partition every hour for 24 hours. And surprisingly for this application, the customers are getting door knocks from all over the world and happen to be on a very regular basis. So every partition happens to be exactly the same. Very strange, but I guess when you're in the door knocking business, this is common. So once we've got 24 hours of these, we basically start dropping the old ones and creating new ones. But that basically removes some space and adds some space, so you end up at no net space change. But oh wait, what happened here? Thanksgiving happened. So there was a couple hours during Thanksgiving where the number of door knocks went huge, right? So this caused a doubling of our storage space. But we're partitioned, right? So we're going to get this space back at some point, maybe. I won't have to tell the boss that we're paying for twice as much storage. So over the next 24 hours, we drop and we create new partitions, no net change. And then finally, we get to the point where we get to drop the spike. And what you see is, you see the used space inside the database do exactly what we expect to do, going back to normal. But on most databases, that orange line, what you're going to be charged for storage, is going to stay the same because your file system has grown. Your storage underlying for, let's say, EBS has grown and doubled. So you're basically now paying 2 extra storage costs until you use this storage, until your business grows, right? So this isn't great. But now with Aurora, we have dynamic resizing, so it's different. Now the blue line basically ends up being exactly as we showed before. The use space drops dramatically, but the major difference is how much the storage space on the back end is using also drops. Now it's not quite at the blue line because we do drop in chunks, so we're not going to get every last little bit back. But what you can see is that you get most of it back, and you're probably going to use that tiny bit up, shortly anyway. So it doesn't actually make a difference. So this is really nice that you don't have to think about growing or shrinking space anymore on Aurora. Let's talk about some of the changes and additions in the replication space with Aurora. So in version 10, we added support for logical replication. What logical replication does is takes the wall segments, the physical binary changes, and converts it into logical statements like updates or inserts. And so this is useful for flowing the changes from your database to something else. So what you could do is get an EC2 instance, and you could turn on logical decoding, and you could extract those changes and then send them somewhere like Kinesis. Or better yet, you can use a built service like DMS, or database migration service, to do the same thing. And you can send it to RDS, you can send it to S3, you can send it to Dynamo, Redshift. There's many places that it can go. Now that's really handy, but it requires you to set up another service, and that's maybe more than what you want. With Postgres now, they've added support for publish and subscribe directly to other Postgres instances. So since version 10, we've had that. We also recently added PG Logical, which is similar but adds some additional capabilities in this space. So you have your Aurora instance, you have your Postgres instance, could be on EC2, and you can now set up a publish and subscription between these two databases with no extra machine that allows you to flow that data. And you can do that to RDS Postgres or Aurora, and even the same database within Aurora you can connect to. Now, the other thing that we support is Postgres extensions. And this is another way to flow data or information from your database to another database or another service. So here I have my Amazon Aurora database, and I'm connecting with one of the Postgres default extensions, Postgres FDW, or foreign data wrapper, sometimes called database links. So this allows you to do things like select, insert, update over this foreign data wrapper and talk to another Postgres instance, for example, an EC2 instance, or an RDS instance, or a Redshift instance, because it does talk Postgres, an older version, but still Postgres. And you can obviously talk to another Amazon Aurora database. And this is whether same version, different versions, it works. So we also added additional functionality. We added an S3 export extension that allows you to directly export tables basically from your database to S3, and you can use them in a whole bunch of other services. But you can also export functionality now by talking to Lambda. So you can trigger and call Lambda functions that can do all kinds of other external processing based on database actions. We added support for ML in the last release last year. And so now you can call SageMaker or Comprehend and do machine learning as part of your database function as well. So you can see how with all these extensions you can start to do much more with your database and move your data around into a whole bunch of different services. So this is very useful. The other area that we spend a lot of time is working on cross-region replication, or what we call global database with Aurora. So if you look at standard Postgres, you'll see that you have basically instances in both regions, right? Region A and region B. And when you want to do an update and replicate between them, you're going to do asynchronous replication between these. This works quite well, but remember that in our regions, they're all over the world. So some of them are pretty close, maybe 12 milliseconds apart. Others are very far away, in the hundreds of milliseconds away. So that pipe, when you're sending a transaction through it, can have challenges, right? You can have timeouts, retries, you can have bandwidth constraints. And you have this single pipe, which means sometimes you'll see a lot of latency and a lot of delay on getting that shipped, or you won't be able to drive the throughput you want. The other challenge with this model is that you need this node over on the destination to process those updates. So this is an additional cost. And what we found is everybody would like to do DR, but from a cost perspective, it's very challenging to support the extra doubling of cost for this. So what do we do different with global database? Well, we have the same region pairs. So we have region A and region B here. So what we're going to do is we're going to add a destination for this cluster. So what we see is we fire a new set of storage in the destination, and we have replications and server and replication agents that have been added. So those are the gray boxes. Now these are completely behind the scenes. You don't have to worry about them. You don't have to manage them. It's all automatic. Now what I'm showing is these single sort of green lines showing that replication, destination. But in fact, it's not single lines, right? It's actually many paths. So because Aurora has segments and chunks, we can do things in parallel, including this kind of replication. So we no longer have to have this single stream replication that can be affected by long latencies or inherently unstable, networks. So when we get a transaction, it's going to flow down to all the regular places, but it also sends one to the replication server, which it sends it across the replication agent, which then puts it in Aurora storage. And at that point, you have DR, and you'll notice that you have no read-only nodes. So this dramatically changes the cost model for doing DR. So you and your boss are happy because you're protected, and it didn't cost a lot, and it's really easy to have because all you had to do is make a few clicks. But let's say you want some read-only nodes. Well, that's really easy. The replication agent can also send those updates to the RO nodes, and you can support those. And you, of course, can have a number of them for different applications. You can do read offloading, or you can do local reads for latency sensitive applications. So this works really nicely. The other thing is Aurora storage can actually talk from the storage to the replication server to the agent to the other storage. And this is handy if the read-write node, for example, didn't get one of its packets to the replication server. So we can catch up storage to storage. Again, part of the continuous repair we do on Aurora storage. So if, for example, something is happening in region A, or you just want to promote region B, it's just that simple. You call promote command, and we'll tear down those replication agents and servers, and we'll promote one of your RO nodes to read-write node. And this takes a couple minutes, and now you're completely functional in another region. And of course, you can have more than one region. So here I'm just showing the two, but you can add a third region with more or less RO nodes, and you can even add another region with no RO nodes. So this allows a lot of flexibility in how you want to design DR or worldwide read scaling. Let's talk a bit about what's changed in performance with Aurora this year. So first, let's talk about our R5 instances. So our R5 instances, when you get to the largest classes like the 16XL and the 24XL, have two sockets. And so you have a bunch of vCPUs in each of those sockets, and they have local memory. And so if you're reading from one socket, from one of the vCPUs, and you're looking at its memory, that's a local access. But if you have to go across to the other memory, it's called a remote access. So guess what? That's what we call non-uniform memory access, or NUMA. So this causes a bit of a slowdown when you start getting into these multi-socket systems. Now it's not a lot, but it does add a bit of delay and can cause a little bit of top-end scaling loss. Conversely, with our Graviton2 instances, R6G, we don't have that because we only have a single socket. So here I'm showing the 16XL of the R6. So it has 64 vCPUs, and its memory is local. Now, this is an oversimplification, just like the previous slide, in that it's a matrix memory model and there's a lot of other complexity, but from your perspective, the main takeaway is it's local, it's uniform, right? So you won't see this change as you go from like a 8XL to a 16XL. You're going to see very linear performance characteristics. The other major difference is that on an R5, when you have two vCPUs, one of them is going to be an SMT or hyper-threaded CPU, right? So when we add work to a CPU, in this case I'm showing a bit of work showing up in CPU 1 and CPU 2, it's going to have to go and be processed, and there's some shared execution resources. So if it's like this example where there's a bit of time between them, it's going to look like you're getting two full CPUs, you don't really see any difference, right? But if you get the full work coming in, then what happens is those shared resources are busy and can't execute, and so it takes longer. So this looks like it's running slower, right? You get less throughput. Conversely, on the R6G with Graviton2, we have two full vCPUs. So when that work comes in, they both go to full CPUs and they get done sooner. Why do you care about this? Well, let's look at a benchmark to see. So here to kind of illustrate a sort of a heavy CPU application, I built a 1,000-row range scan that then nests to a couple other tables and also joins to another 1,000 sets of rows. And sort of the vertical axis is queries per second, so higher is better. And in the blue, we have the R6G, and in the purple is the R5. And these are largest, so basically 2 vCPUs. And connections on the bottom are sessions. So at 1, both of these are on 1 vCPU. They're burning a full CPU, and they're full, they're regular CPUs. So they're going to be very close. But then as soon as we move to 2, what we see is a dramatic difference. The hyper-threaded CPU only picks up about 30% improvement, right? But the Graviton CPU basically doubles. And so we see a 70% difference between these two large instances based on the full CPU as opposed to a hyper-thread. How does this look on an application that's not completely CPU bound? Because that's not everybody has those. So we took HammerDB, which does I/O, does writes, and we ran that test. So on the vertical axis is new orders per minute. And so again, higher is better. And then this time we're using extra largest, so they have 4 vCPUs. The blue is still the R6 and the purple is the R5. And what we see as we get towards the top end, we see about a 15% performance improvement for the Graviton2 over the R5s. And this is because we still are seeing some of the CPU benefit, even though there's other things to contend with like I/O. Now, remembering that the R6 is also cheaper than the R5, so even if it's just 15%, it's 15% plus the price difference. So your price performance is probably going to be quite a bit better. On the R6s, or on the larger instances, like we have here, I'm showing the 16 XLs as well as a 24 on that same, my first benchmark, right? So again, what we're going to see is that at 32 vCPUs, these are very similar because they're all on full CPUs. But as we move off, and now we're talking about using hyper-threading on the R5s, we see the 16XL for the R6 being 50% faster because it actually gets full gain. Now, the interesting thing is that we notice that the R6 still outperforms the R524 even though it's got more vCPUs. And this is because it has to contend with both hyper-threading and NUMA, which means it doesn't double over its 16XL, in the same way. So if you don't need the extra memory that you get with the 24XL, the R6 16 is a really good deal and shows that Graviton2 is great for high CPU use cases. So let's go talk a bit about how you can use these. Well, the nice thing is you can actually have heterogeneous clusters where you can have a mix. So you can start with all R5s, you can do a modification, and you're going to get an R6G. If you like that, then you can make it fail over and make it your read-write node. And then once that's tested, you can make all of them R6. So it's really easy to make that change and migrate to the R6Gs. Talking about migration, how do you get to Aurora Postgres? Well, there's a bunch of these that you can use. If you're coming from a heterogeneous source, DMS is the best thing. SQL Server to Oracle to Aurora Postgres, we've done a whole bunch of those conversions internally. It works great. If you're just coming from Postgres, pgdump or restore or logical replication is good. But the one I'd recommend if you're coming from Aurora, or coming from RDS Postgres, is to go and use our read replica. Let's dive into that. So here we have our service connected to RDS Postgres. This works great, it's working away, but now you want to move to Aurora. So you do a create read replica, and this is going to create a new cluster, and we take a snapshot. That snapshot gets converted into an Aurora instance, and so that's up and running, and then we catch up via asynchronous replication. Once that's all done and your lag is really low, you can stop your application, wait for those last transactions to flow over, and then you promote your Aurora instance into a full cluster and move your service to it. And then you're done. And that's it. So with that, I'd like to mention that some of my colleagues have some other sessions they'll be presenting. If you want to see some other information on Aurora, thank you very much. And remember to fill out your session survey.